So the system number one, if you have this number 6 here. Number 5, this one has its own natural frequency. That one is its own natural frequency because that's omega is square root k over n. Think about that way. This one too. See if you can get that makes sense. Because eigenvalue 1, eigenvalue 2. One eigenvalue 1 will be closely related to this one. Another eigenvalue will closely related to this one. But they couple together, both of them will get different damping because I changed this one. And this one has its own damping, but very small damping, system-wise. That's the purpose. And later on, I will show you how to design a desired closing eigenvalue. We call a Paul placement technique. But this one just for you to try out. Okay. Any other questions? No. Finish up to here, right? Yes, last week. We finish here, yes. Last week we get to this point, and I think we did not get into the cross-state series of discrete time model. Now, as soon as we get discrete time model like this, that is not differential equations. That is just algebraic equations. It's easy to solve the solution for this system. So that is something that in your number 6, problem number 6, how can you do the simulations from your discrete time model? What you have to do is like this. You just set k equal to 0. Then you got ax0 plus bu0. And assume, now in the homework number 6, of course I assume that x0 equal to 0. If you don't know that, you assume that equal to 0. Alright? And then I give you the u, that's ag. Right? bag. Now you have to figure out your b. What is the b? And u here, now in homework number 6, just like your a sub g. That's your input. Then you can just sub into your equation like this. Then you say x0 equal to ax0 plus bu0. And if you know ag equal to cosine omega t, 10 sine omega t or cosine omega t, you just sub in here. And now this k0, the k0, that's your initial time, right? That's initial time. Alright, and k equal to 1, that means k times delta t. That means k times delta t, that means delta t. Alright? K equal to that k delta t into delta t, right? Because of those k, I just ignore the delta t, those things. And if you keep sub into the equations, then you will get these equations. And then, of course, now if you know how to write a program, you can write just x1 equal ax0 plus bu0, and x2 equal ax1 because your x1 already computed, plus bu1, and then x3 is ax2 plus bu2, and so on. This is recursive. It's very easy to solve. As a matter of fact, in your SCI lab, they also have a program for you to use to get all the core solution series. Now, what I'd like you to see is if I sub my x1 into my x1 here, then I will get this. I will get a squared x0 plus ab u0 plus bu1, and a3 x0 plus a2 bu0 plus ab u1 plus bu2. If I keep sub my x1 and my x2 into the x3, then I have these equations. And why I want to do that? I will show you why. If you look at this, continue to do this until you have k equal to k, then the solution series become a k to the power x0 plus a k minus 1 bu0 plus a k minus 2 bu1, and so on. So there's no x anymore in these equations. They all depend on the u. So you look at this. But you have the power of a. And a k x0. Look at that term. Okay. A k x0. That's the term. A k x0. You need to look at that term. A k x0. And so if x equal to 0, now if x 0 equal to 0, then of course a k x0 equal to 0. And this term is we call transient. That's a transient. That means when you have initial conditions, then you have that term. If you don't have initial condition, then you don't have that term. That's a transient. This is what we call transient response in discrete model. That's a transient response. All right. Now, however, if the system is stable, all right, then all eigenvalues, I should say that in the discrete model. This is discrete model. That means the absolute value of all eigenvalues will be less than 1. Will be less than 1. All right? Now, if that's the case, when k going to sufficient large, then ak x0, x0 will approach to 0. All right. Now, in the discrete model, not the discrete model here. A is a discrete model. This is the continuous time model. The discrete model, the stable system, all the eigenvalue, the absolute value of all eigenvalue, not less than 1. Why? Tell me. Why? divide all the eigenvalue, the absolute value of all the eigenvalues in one. Anybody think what?
Because this time it's
Yeah, A equal to exponential AC delta T, right? Alright. Now AC, this AC, the eigenvalue of AC, so eigenvalue, eigenvalue of A will be equal to exponential the eigenvalue of AC times delta T.